So now we move on to more rotational equilibrium and rotational dynamics in Chapter 8. So a lot of this is going to be familiar to you. It's just going to be cast in a different light, okay? Instead of linear, rotational. So we're going to introduce torque and how the second condition of equilibrium then can be used to help us solve for torque. The concept of center of gravity. We're going to look at examples of objects in equilibrium. So there's our statics portion. Relationships between torque and angular acceleration. And then rotational kinetic energy. So we're back to the energy again. So we've gone from force to energy and angular momentum. So in defining torque, the tendency of a force to rotate a body about some axis is measured by a quantity called torque, and we use the little Greek letter tau to represent torque in our relationships. The torque due to a force, so there's our force, has a magnitude of force times distance. So we're back to, again, our same definition of force or work as force times distance. Now we have to deal with something, though, called a lever arm or a moment arm. And so when we deal with rotational dynamics, we have to look at things a little differently because of our lever arm and the distance from where the force is being applied to the point where we have a pivot or in this case, a hinge. We're looking down on the top of a door. We can see the hinge on the left side, and we can see the force being applied at the doorknob to open the door. So the lever arm is the perpendicular distance from the axis of rotation to a line drawn along the direction of force. So we have to develop this a little more because we have those components again, sine and cosine, to deal with. So if we look at a door and instead of pushing on the door to open or close it, we grab the doorknob and we're pulling on it. In pulling on the door, we have no rotational dynamic. And so all of our force is along the x-axis. And in doing this, the door goes nowhere because as you pull on that door, there's an equal amount of force at the hinge holding it in place. Okay, so it's pretty much static. It's not going anywhere. Unless you pull hard enough, you're going to rip the doorknob off or you're going to rip the door off of the hinges. So normally what happens in the situation of a door is you're trying to turn the knob and open the door by pushing or pulling. So it's only the component in the y direction or the sine of theta, in this case, that's actually going to give us any work and motion when we try to do this. So we've got some radius to the doorknob, we've got some force being applied, and because it's applied at some angle, force sine theta, we will actually get some work or force done or torque out of this. So what happens here is that we've got some distance that we are going to apply to get this torque going here. So as you can notice, as we change the angle, let's bring that angle down on the x-axis, you can see we lose all of our distance. But as we start increasing the angle all the way up to perpendicularity, we increase our value of d. So d, the radius times the sine of theta, starts giving us then what we're looking for in terms of the work or the torque in actually opening or closing the door. So let's switch gears here to a wrench. We've got a wrench that is locked down on a nut here, and we're going to try to move the wrench to tighten or loosen the nut. So the applied force F acts at an angle, in this case phi, with the horizontal. Okay, so we're trying to pull up, but we're not exactly pushing straight up, we're at kind of an angle. The lever arm then is the distance d, not the length of the wrench. So you can see that down here. This distance down here would be considerably shorter than that of the length of the wrench. So D is the perpendicular distance from the axis of rotation to the line along which the applied force acts. Okay, so there it is right there. You can see the perpendicularity being displayed. So D is related to L, the length, by the expression D is equal to L sine phi. So we've seen that before, where before we had L cosine, now we have L sine because we're moving it. We're getting all of our torque in the y direction. The net torque produced by the force F then is given by tau equal to force times the lever or the length of the wrench times the sine of theta. So the idea here is to go back to our vector mechanics here and resolve the force then into its component. One component is going to give us no work. The other component is going to give us all of the work. The torque about the axis of rotation then produced by the component F cosine phi is 0. There's no torque, there's no work, because the lever arm of this component is 0. Okay, if you took the cosine of phi, it would come out to 0. But the component F sine phi has all of the torque, and it has a lever arm of L. So if we determine what this was, it looks to be about 45 degrees. We took the sine of 45 degrees, we'd get a value of about 70% of what the force is, and that would give us then our component doing all the work. The torque produced by this component, tau, is equal to force times the length times the sine of phi. So in rotating dynamics here, what we need to do is we need to look at all of the forces applied to an object. In this case, we've got an irregular shaped object that we're going to apply two forces, force F and force F1 and F2. You'll notice here that they are pretty much opposing, but the amount of force applied will be determined by the amount of force times length times sine of theta. So F1 tends to rotate the object counterclockwise. So you can see counterclockwise direction. Force 2 tends to rotate the object clockwise, the opposite direction. So the force position will determine which one of these wins the battle, F1 and F2. So the net torque acting on the object about this point of rotation here, 0 or O, is found by summing the torques. So the summation of the torque, just like the summation of the forces, in this case tau 1 and tau 2, are summed together by their component forces F1 plus F1 times distance 1 plus F2 times distance 2. The units of torque are forces, and that's the force times length, and we're back to Newton meters, or a kilogram meter per second squared, because that's really a mass times acceleration relationship, or a foot-pound. So let's look at an example, a spinning crate. A packing crate is being pushed by two equal and opposite forces. Find the net torque exerted on the crate if its width is 1 meter. Assume an axis of rotation through the center of the crate. So we've got everything laid out on the diagram here. Force 1, 500 meters. Force 2, the exact 500 meters. You'll notice that they are in a position here so that they are opposing each other. Okay, we have 1 meter of distance, and so our distance D1 and D2 will be half of that amount. So if we sum all of our forces here, you can see tau 1 and tau 2, force 1, distance 1, force 2, distance 2, we end up with minus 250 Newton meters in this case. And when we sum them, we get minus 500 Newton meters. Let's go back to our swinging door representation here. Find the torque produced by a 300 Newton force applied at an angle of 60 degrees to the door. So there's our angle, there's our force, there's our length, we need to determine what the distance is going to be. So in this case, find the torque produced by the 300 Newton force at an angle of 60 degrees. Again, we break it into our components, F sub x, F sub y. F sub x cosine 60, F sub y sine of 60 is going to give us 150 and 260. So we can see here, once they're resolved, the 150 Newton component does nothing to rotate the door. But the 260 Newton component is what's going to open or close the door in this example. So we end up with an amount of torque of 260 newtons times the distance, 2 meters, which gives us a 520 Newton meter amount of torque. Notice in this case, the entire length of the door is in fact our lever arm. So when we come back, we're going to take a look at torque and satisfying the second condition for equilibrium.